Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, India. Today we are going to discuss about a module called X-ray photoelectron spectroscopy that belongs to the chapter Spectroscopic Methods under the paper titled Characterization Techniques for Materials 2. So students, let us see what we are going to learn in this module. First, I will give you some introduction to the spectroscopic methods and the instrumentation of X-ray photoelectron spectroscopy will be studied in the next. And finally, we will see how we use this XPS spectroscopy for elemental analysis of the materials. The spectroscopy is the study of interaction between the electromagnetic radiations and the matter as a function of energy. Historically, the spectroscopy referred to the use of visible light dispersed according to its wavelength using a prism. Later, the concept of variable energy and Einstein's relationship of E is equal to h nu, where h is the Planck's constant and nu is the frequency, was realized. This concept extended to comprise a measurement of any quantity as a function of either wavelength or frequency. The plot of responses with wavelength or frequency is referred as spectrum. We use spectroscopy to study the nature and behavior of electrons in the material composition. Photoelectron spectroscopy is a technique generally used for determining the ionization potentials of the molecules in the material. It involves the measurement of kinetic energy of photoelectrons to determine the binding energy, intensity and angular distributions of these electrons, and use this information to study the electronic structure of the molecules. It differs from the conventional methods of optical spectroscopy, where the electronic structures of a material is studied by exciting electrons from an initial low energy state to a higher state with absorption of photon energy from a spectrophotometer. If the wavelength of the incident beam has enough energy to promote an electron to a higher level, then we can detect this in the observance spectrum. Once in the excited state, the electron has higher potential energy and will relax back to a lower state by emitting photon energy. This is called fluorescence and can be detected in the spectrum as well. In contrast, in photoelectron spectroscopic technique, it measures the energy of photoelectrons emitted from solids, gases or liquids by the photoelectric effect and provides the quantitative and qualitative measurements for understanding the electronic structures and chemical composition of the material. The electrons exhibit characteristics energy levels, revealing the nature of chemical elements in samples being examined. The technique will be discussed with focus on instrumentation and analysis of the recorded spectra for elemental analysis. The XPS technique is based on Einstein's idea about the photoelectric effect developed around 1905. The concept of photons was used to describe the ejection of electrons from a surface when photons were impinged upon it. During the mid-1960s, Dr. Seghban and his research group developed the XPS technique. In 1981, Dr. Seghban was awarded the Nobel Prize in Physics for the development of the XPS technique. Depending on the source of ionization energy, the photoelectron spectroscopy can be divided into two categories. First, with the ionization triggered by the valence electrons using energy of ultraviolet rays, whose energy is less than 40 electron volt, which is sufficient to eject electrons from the valence orbitals, is referred as ultraviolet photoelectron spectroscopy UPS. The second one, when the ionization is triggered by the core electrons using high energetic X-rays with energies 1000 to 1500 electron volt that could eject electrons from the core and atomic orbitals, is referred as X-ray photoelectron spectroscopy. The XPS spectroscopy. Here, the photoelectrons can only escape from the uppermost atomic layers of solid because their energies are relatively low. Thus, electron spectroscopy is a technique for surface chemical analysis due to the short range of the photoelectrons that are excited from the solid. The energy of the photoelectrons leaving the sample is determined using a CHA, and this gives a spectrum with a series of photoelectron peaks. The binding energies of the peaks are characteristics of each element. The peak areas can be used with appropriate sensitivity factors to determine the composition of the material's surface, the shape of each peak, and the binding energy can be slightly altered by the chemical state of the emitting atom. Hence, XPS can provide chemical bonding information as well. XPS is not sensitive to hydrogen or helium, but can detect all other elements. Now, let us study the working principle of photoelectric effect. The photoelectric effect states that the electrons can be knocked off the surface of a solid by electromagnetic radiation. The ejected electrons are called photoelectrons. Here, the absorption is very fast, about 10 to the power minus 16 second, Originally, the photoelectric effect was first observed by H. Hertz in 1887 when Hertz noticed that sparks would more readily jump between two charged surfaces that were illuminated with light. The Hertz observation would ultimately lead to Einstein's photoelectric law that says the kinetic energy of an emitted photoelectron could be given by Ek is equal to h nu minus Eb minus phi, where phi represents the energy required for an electron to escape from a material's surface, h is the Planck's constant and nu is the frequency. The X-ray photoelectron is an electron ejected from an electron cell of an atom when atom absorbs an X-ray photon. The value of phi depends on both the sample material and the spectrometer binding energies of atomic electrons have characteristics values. These values are used to identify elements. The following points are noticed in the above description for XPS. The first point is that no photoemission could observe for energy h nu less than phi. Second, no photoemission could observe for levels with binding energy plus phi greater than h nu. The third point, kinetic energy of photoelectron increases as the binding energy decreases. Fourth, the intensity of photoemission is directly proportional to the intensity of photons. 5. A range of kinetic energies can be produced if valence band is broad. 6. Since each element has unique set of core levels, kinetic energy can be used to fingerprint the elements. Now, Kopman has given theorem that reads the binding energy of an electron is simply the difference between the initial state, that is the atom with n electrons, and final state with atom that has n-1 electrons and free photoelectrons. So, the binding energy is equal to the energy of final that contains n-1 electrons minus energy of the initial value which is containing n electrons. If no relaxation followed photoemission, the binding energy is equal to negative of the orbital energy, which can be calculated from the Hartree-Fock concept. The photoemission process often has three steps. First, the absorption and ionization. This is the initial state effects. The second one, the response of atom and creation of photoelectron, which are the final state of effects. And then third is the transportation of electron to surface and escape, that is the extrinsic losses. Now let us discuss about the instrumentation for the XPS. A modern instrument of electron spectroscopy contains both the XPS and AES in a single chamber as a multifunctional surface analysis system. The figure below shows schematically the diagram of XPS that includes an electron gun, an X-ray gun, and a said analyzer of electron energy. The details of these parts are discussed below. The instruments for electron spectroscopy require an ultra-high vacuum environment with a pressure in the range of 10 to the power minus 8 to 10 to the power minus 10 millibar, where 1 millibar is equal to 1.33 torr. The reason for using ultra-high vacuum is to reduce the chances of low energy electrons being scattered by gas molecules on their way to reach the detector, and to keep the sample's surface free from gas molecules contamination. Low energy photoelectrons and Auger electrons are easily scattered by gas molecules. Scattering will reduce the signal intensity and increase background noise in spectra. The high vacuum chamber is commonly made from stainless steel, and joints of chamber parts are made from crossed copper gaskets. Ultra high vacuum can be achieved using diffusion pumps, sputtered ion pumps, or turbomolecular pumps. Magnetic shielding is also required for chamber because trajectory of signal electrons is also affected by magnetic field. The second component of the X-ray spectroscopy is source guns. There are several source guns. The first kind is of X-ray gun. An electron spectrometer system contains an X-ray gun for XPS analysis. The X-ray gun produces a characteristic X-ray line to excite atoms of the surface to be analyzed. The XPS uses monochromatic and non-monochromatic X-ray sources. The output from non-monochromatic X-ray sources consists of a continuous energy distribution with high intensity of K alpha characteristics lines. The monochromatic sources produces output by removing continuous X-rays from a radiation spectrum. The energies of aluminum K alpha and magnesium K alpha are 1.4866 and 1.25 kiloelectron volt respectively, which is lower than the energies of copper K alpha line, which is 8 kiloelectron volt, and molybdenum K alpha line, which is 17.44 kiloelectron volt, and normally used in X-ray refractometry. The reason to choose lower width of X-ray is their narrow line width. The line width of characteristics X-rays refers to the range of energy. The XPS requires a line width less than 1 electron volt to ensure good energy resolution. Both K alpha of aluminum and magnesium exhibit line widths less than 1 electron volt and also have sufficient energies for photoelectron excitation. Second one is electron gun. The electron guns used in AES analysis is similar to those used in electron microscopy, and field emission guns are commonly used in electron spectrometers. This provides an electron beam of high brightness with spatial resolution of 200 nanometer, and LAB6 is generally used as a source. The field emission guns provides superior brightness and higher spatial resolution than LAB6, and also their emitting surface remains clean during operation without absorption of gas molecules. Third is ion gun. The function of ion gun is twofold in XPS. Firstly, it provides high energy ion flux to clean sample surfaces before examination. Sample surfaces are commonly contaminated with adsorbed hydrocarbons, water vapors, and oxides that need to be removed before surface analysis. The second function is to sputter out sample atom layer by layer so that an elemental depth profile can be revealed. The ion gun produces an argon ion beam by either electron impact or gaseous discharge. Electron energy analyzer. An XPS spectrum is obtained by an electron energy analyzer. The most commonly used analyzer is the concentric hemispherical analyzer, termed as CHA, also called hemispherical sector analyzer, HSA. The analyzer is composed of two concentric hemispheres with radii R1 and R2, and its working principle can be understood from the figure. Negative potentials V1 and V2 are applied to inner and outer hemisphere respectively. The applied potential generates a median equipotential surface with radius of R0. The potential along the median surface V0 is called the pass energy of the CHA. A slit at one end of the CHA allows electrons from the sample to enter, and a slit at the other end of the CHA lets the electrons pass through to an electron detector. The electrons are focused by an electrostatic transfer lens before being injected into the CHA, and their energies are reduced to a certain level. Electron energy reduction by electrostatic processing is called electron retardation. The electrons can be analyzed by one of two modes: the constant analyzer energy, which is CAE mode, or constant retarding ratio, or CRR mode. Commonly, the spectrometer is run in the CAE mode for XPS and CRR mode for auger of the spectroscopy. The CAE mode maintains the pass energy of the CHA as constant. The electron energy are analyzed by recording the change of electron retardation. An XPS spectrum is a plot of intensity versus binding energy. Photoelectrons are ejected from different electronic cells and subcells. Each binding energy peak is marked as an element symbol plus a cell symbol from where the photoelectrons are emitted. Example: aluminium 2p, oxygen 1s. The photoelectrons emitted by subcells of P, D and F are commonly marked with an additional fraction number, for example, copper 2p half. The XPS spectra can have three types of peaks on a background: photoemission from core electron levels, photoemission from valence levels, and Auger emission excited by X-rays. The figure shows an XPS spectrum of a clean silver surface in which the core level peaks are marked as 3s, 3p and 3d. The valence level peak is marked as 4d and Auger peaks are marked as M and N. The core level photoelectron peaks are the prime peaks for elemental analysis. The valence level peaks are those at low binding energy and are primarily useful in studies of the electronic structure of materials. The Auger peaks arising from X-rays excited Auger processes are useful for chemical analysis. The XPS spectrum also include extra or satellite peaks associated with main core level peaks as shown in the figure. Satellite are the extra peaks which result from interaction between a photoelectron and a valence electron. A photoelectron can excite a valence electron to a high energy level and thereby lose a few electron volts of kinetic energy. This will create a satellite peak associated with a core level peak of photoelectrons. The sake of satellites are useful for chemical analysis. For example, a satellite is associated with the copper 2p of CuO, but it is absent around the Cu2p peak of Cu2O. So students, let us summarize what we have learned in this module. Here in the introduction, the basic principle of spectroscopy and electromagnetic spectrum with various kinds of interactions have been discussed. The introduction and principle of XPS that depends on the photoelectric effect with schematic diagram have been discussed. The instrumentation of XPS with main parts of XPS as electron gun, ion gun, X-ray gun and electron energy analyzer has been discussed, and the basic spectrum of XPS with example of spectra of clean silver surface has been demonstrated. Thank you.